everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll continue our discussion on the Laplacian matrix, and today will be our third lecture on it. So in the first lecture, we introduced or defined what a Laplacian is, and we also talked about some nice properties that we can derive from this definition. In the next lecture, we discussed an example where we can actually use the Laplacian matrix to model the behavior of a system. In today's lecture, we'll again discuss some new properties of the Laplacian matrix, but these properties now depend on the topology of the graph that we are dealing with. Meaning, sometimes the topology of a graph can lead to some more interesting properties of the Laplacian, which is something that will be the focus of today's lecture. So let's get started. We start with a property which pertains to the row sums in Laplacian matrices. Let us first write what the property exactly says. It says, or it talks about, zero row sums. It says that let G be any digraph. It doesn't need to be strongly connected, no aperiodic, none of those things. It can be any general graph. Let's say containing n number of nodes. The Laplacian matrix is denoted by LG, or we can simply write it as L. Then, irrespective of the size of the digraph, the topological properties of the digraph, something that always holds is this. L times 1n is equal to 0n. What is 0n? 0n is simply an n cross 1 vector which has all of its entries as 0. And what does L1n do? L1n, so again, we already know this, we have used it several times in the past. 1n is nothing but an n cross 1 vector containing all of its entries as 1. This. So effectively, L1n again, we have used these kind of formulations several times in the past, especially while pertaining to the adjacency matrices. What we know is L1n simply gives us a vector again, where each vector is nothing but the ith row sums. So what this result here means is that every row sum that we take must be equal to 0. Again, this is something which can be very simply proved and follows directly from the construction of a Laplacian. So this is going to be extremely easy. So we'll do it rather quickly. Let's start with the proof. We say that let's start by calculating what exactly is L1n. So let's write it. For given digraph, L1n is simply equal to, let's write it here, this is L11, L12 up to L1n Similarly, we have, let's say, some ith row, Li2 going up to Lin, and the last one would be Ln1, Ln2 going up to Lnn. And 1n again is nothing but a vector of all with all entries being equal to 1. Now this product is equal to, this implies L1n simply gives us a summation, which is equal to L1 times j, where j varies from 1 to n. Similarly, for the ith row, again, as you can see, this gets multiplied with this, and is again simply the sum Lij, where j varies again from 1 to n. And the last entry similarly becomes Lnj, again j varying from 1 to n. So how is this equal to the zero vector? Let's see that. In order to understand that, let me copy this expression again and write it here. For any given Laplacian matrix, we know that the following property holds. What is that property? Let me start by writing the definition. It is d out minus a. This implies that L again, this is something again that we'll keep using. L again is equal to the first entry, L11, is nothing but, so we refrain from writing the diagonal entries as D out. Why do we refrain from writing it as D out? Is because, again, remember that the Laplacian matrix does not give us any information about the self loops, or in fact, even cancels any, like, let's write it here. Say if we have a self loop, then the self loop again gets added because of D out, and again gets subtracted when we do minus of A, meaning effectively the self loop vanishes, meaning L11, let's write it here, for the ith entry, L11 is simply equal to D out of 1 minus of A11, and Lij, such that j is not equal to 1, is equal to minus of A1j. Okay. So what happens now? What happens is, let's write it. Because of this, we can generalize the expressions as this. For the ith row, Lii is simply equal to D out of I minus Aii, and Lij, such that j is not equal to I, is equal to minus of Aij. So now if we add it up, what do we get? Just remember that the first expression that we see here, let me bring this here. The expression that we see here is simply equal to summation of all of the aij's, where j varies from 1 to n, but is not equal to I. This boils down to this. If we look at this expression again, L1n is simply equal to the row sums. So, thus, ith row sum becomes summation of Lij, where j varies from 1 to n. Again, we can split it into the sum of two different terms. The first is simply Lii, and the other is summation of Lij's, where j varies from 1 to n and is not equal to I. The reason why we did that, because we already know that they have two different forms. Substituting this here, we get Lii is summation of Aij, j equal to 1, j not being equal to I, up to n. Again, summation of j equals 1 to n, j not equal to I. Lij here is simply equal to minus of Aij. So let me start with this being minus, and this is Aij, which becomes equal to 0. Implies what we found is every row sum adds up to 0, or every row sum is equal to 0. Implies L1n equals 0n. Hence, true. So we can conclude something interesting from here, which again follows quite straightforwardly. That is, we have L1n being equal to 0n. What this also implies is, now again, 0, 1n can be written as the scalar 0 times 1n, which implies that every Laplacian matrix has 0 as an eigenvalue. Furthermore, the corresponding eigenvector equal to 1n. So this is also yet another interesting property which holds for every Laplacian matrix. A few questions arise from here. So these are the questions we will try to answer in today's, one of them at least we will try to answer in today's lecture. Let me pose the first question. It is, we know that Laplacian matrices have 0 row sums. or what kind of digraphs do they also have zero column sums? Meaning, while it is natural that every row sum is zero, now, is it possible under some scenarios that the column sums of Laplacians or Laplacian matrices also become equal to zero? Under what conditions does it become possible? So this is one of the interesting questions. Is it related to graph topology, or what factor decides this? Or is it even possible? Now the second question is, we know that 0 is an eigenvalue of every Laplacian matrix. But we do not really know at this point if this 0 is a simple eigenvalue or a semi-simple eigenvalue, or it is simply corresponds to a defective Laplacian. Meaning, the algebraic multiplicities and the geometric multiplicities are not equal to 1, let's say. Then, which of the following is true? First, is 0 always a simple eigenvalue? Let's write it. A simple eigenvalue. Meaning it occurs only once. That means every other eigenvalue would have to be non-zero. Is it always true? The second is, if not, let's say it is not a simple eigenvalue and is repeated. Or we can write, if 0 is a repeated eigenvalue, is it semi-simple? Meaning all the Jordan blocks corresponding to this eigenvalue have a size equal to 1. And the third, and perhaps the most important question is, what are the factors which determine such spectral properties of a Laplacian matrix? So in today's lecture, we will not answer all of these questions, but we will definitely answer one of the questions, which is the first question. When can a Laplacian also have a 0 column sum for every column? And in the next lecture, we'll answer question number 2, which pertains to 0 being either a simple eigenvalue or a repeated eigenvalue. So let's get started with the second part, which pertains to 0 column sums. In Laplacian matrices. Which goes this way. Let G be a weighted diagraph containing n number of nodes the Laplacian matrix as before is denoted as L of G. Having said this, let us now state our results. We say that LG has 0 column sums whenever G is a weight balance diagraph. This highlights that the weight balance property of a diagraph ensures that not just the row sums, but the column sums and Laplacians can also now become equal to 0. So let's quickly remind ourselves of what is a weight balance diagraph. So before we get to the proof of this, let me explain, do a quick recap of a weight balance diagraph. For a weight balance diagraph, the in degree of a node I is equal to its out degree for every I belonging to 1 to n, meaning whichever node we pick, its in degree equals its out degree. Let's see a quick example. Let's look at the diagraph shown here. Okay. Draw the edges, I'll get them by. This. So there are two outgoing edges, two incoming edges to this, the central node. And let's also draw two more outgoing edges from it. Okay. And this. And that's right. Then let's index the nodes. This is 1, 2, let's use this color, 1, 2, 3, 4, and 5, and the H weights be equal to. So note that we have to make sure that for every node, the in degree must equal its out degree. Let's assign the in degrees for these in the node 3. Then what should be the corresponding out degrees? Again, it must, since the in degree for the third node is equal to 6, its out degree also must be equal to 6. Hence, I can simply assign this. Now, we observe that for node number 4, the in degree is, for node number 5, the in degree is 4, meaning I must add a 2 and a 2 here so that the out degree also becomes equal to 4. Similarly, this out degree here has to be equal to 4 and this here has to be equal to 2. If you notice that for the given diagraph, whichever node we pick, its out degree is equal to its in degree. So now we know what a weight balance diagraph is. Let's come back again to this property and let's try to prove it. So again, the property says that whenever G is weight balanced, LG, meaning the Laplacian of the graph, has 0 column sums. Let's try to prove it. Zero column sums can be mathematically expressed as one n transpose times L is equal to 0 transpose. So what we have done here is we've simply added the columns by multiplying 1 n transpose to every L. And this here represents that each sum is now equals 0. Let me write here 0n so that we do not confuse it with the scalar 0. Okay. So ultimately, if my diagraph is weight balanced, this must hold. So let's quickly look at, as we did in the previous case, when we were trying to prove 0 row sums, we looked at the ith row. So let's similarly do that and look at the ith column. Instead of writing ith column, please note that the dimension of this is 1 cross n and n cross n, meaning this here becomes a 1 cross n vector. So we say that the ith entry of 1n transpose L is given by one n transpose L into J. Again, this is equivalent to writing L transpose 1n and looking at the jth entry of this. Now we already know what a Laplacian looks like. Let's see what L transpose look like. We know that every Laplacian matrix takes the form So again, we used it directly in the previous proof. So I will write it directly here without, again, discussing too much. So this here is L11, and this becomes minus A12 minus going up to minus of A11. Similarly, for the ith row, this is given by AI1 minus of AI2, and it goes on to minus of AIN. And somewhere the diagonal entry is equal to LII. And similarly, the last row here is equal to minus of LN1 minus of AN2 going up to LNN. And LII is simply equal to summation of AIJs, J going from 1 to N, but not being equal to I. Then L transpose 1N is again equal to, so we take a transpose of the Laplacian matrix and write it as, it is L11 minus A12 going up to A1N. This similarly is equal to, or we keep on going. For the ith column, this is equal to minus of AI1 minus AI2, and somewhere we have LII, and this ends with minus of LIN. And similarly, the last column is equal to minus of AN1 minus of AN2 going up to minus of ANN. This. And now we multiply this with the vector of all ones. So what do we get here? The ith entry is, let's look at the ith entry is given by some column AII, now getting multiplied by this. So what exactly is this equal to? This column here is equal to, let's fill in its entries. This column will have entries in this form: minus AIN, the ith row here will have entries minus of A1I minus of A2I minus of, this is the ith entry, or rather, sorry, this will be LII going up to minus of ANI. Hence, the ith entry now becomes equal to summation of or is equal to minus A1I plus minus of A2I plus LII plus minus of ANI. Hence, we can simplify it again as LII minus of summation of A J into I, where J varies from 1 to N, again J not being equal to I, and we know that LII is simply equal to
summation of A ij, where j is equal to 1 to n and j not equal to I, minus of summation of aji, again j equals 1 to n, j not equal to I. So let's focus on this first term. What does this term represent? As we already know, this is the out degree of the ith node. And this here is in degree of the ith node. And because it is a weight balance diagram, we know that both of them are the same. So what does this imply? This implies L transpose 1n, the ith entry of this is simply equal to 0 for every I, which implies, so we know that L transpose I is nothing but 1n transpose L and its ith entry is equal to 0 again for every I. This simply implies that 1n transpose L gives us the 0 vector transpose, implies column sums of L equals 0, which completes our proof. So, does it give us any information about the corresponding left eigenvector in a weight balance diagram? It in fact does. So the left eigenvector also lies in the span of 1n in the case of a weight balance diagram. So with this, we end today's lecture. And in the next lecture, we'll try to answer the second question, which pertains to the spectral properties of the Laplacian matrix. In particular, we'll talk about the properties associated with the zero eigenvalue of a Laplacian. Thank you.